Hello everyone, welcome to the lecture series of KEC 053 with the subject name VLSI technology as per AKGEC syllabus scheme. I, Rajni Prashar, is going to deliver the lecture on optical lithography. So in the previous lecture we have seen that what is basically the photolithography technique, right? What is basically photolithography technique? That in case of photolithography technique, when suppose we have this wafer, right, we have seen that we have the silicon substrate which we have made with the help of the CZ process. We have learned that, right? Over that we have grown the silicon dioxide layer, right, that is known as SiO2 layer, silicon dioxide layer, that is done with the help of oxidation process, right? With the help of oxidation process we have grown that. Now over this silicon dioxide we have to make some windows, right? See here we have seen that we have to make some windows so that we can implant our impurities under that. Suppose in case of NMOS, we are fabricating a NMOS, we have this p-type substrate, right? Here we know that we have the N plus diffusions, right? So these diffusions are done by removing these oxide layers and then by adding the N plus impurities in the p-type substrate. So that creating a window, that window creation is done with lithography technique. Okay, so this window creation is done with the help of these lithography techniques, and we have seen that there are, depending upon the light source, we can classify it as optical lithography, then E-beam lithography, and then we can also have here X-ray lithography, right? And these, what are the masks which we are going to use for the lithography process? After this lithography process, we have to remove the PR, we have to remove this silicon dioxide layer. This is done with the help of wet etching, and then finally we have to deposit some material which will be covered under the deposition process, right? So optical lithography is a photographic process by which the light sensitive polymer, which is known as photoresist, is exposed and developed to form the 3D image on the substrate. So in case of optical photolithography, we are going to have the UV light as a source, right? And this photoresist material, it should be sensitive to UV light only. Okay. So in general, the idea of photoresist image has the exact shape of the design or the intended pattern in the plane of the substrate with the vertical walls through the thickness of the resist, because over this silicon dioxide layer we are going to deposit the PR material first, right? PR, that is known as photoresist material. This is your silicon dioxide layer, and we have the substrate p-type or n-type substrate, right? So this PR, the thickness of this PR will be calculated by the vertical walls, that how much thick is the PR material which we are going to apply over for this lithography process. So this sequence is generally performed with the several tools which are linked together in a contiguous unit, that is known as lithographic cluster. So for optical lithography we have some steps which can be listed, as the very first step is the substrate preparation. Right, we have prepared the substrate. This substrate should be very much cleaned. So cleaning of this substrate should be done, that we are going to see in the upcoming slides, that how the cleaning is done, what are the methods which are used to clean the substrate. Then the photoresist spin coat is applied. Here we can see that photoresist is applied. Then it is baked up to a certain temperature, so that this liquid PR material is in the dry shape and it is properly pasted over the substrate. then it is exposed and aligned. Here we have the mask. This is the mask. This mask will be engraved over this p-type, over this substrate, and we are passing this UV light. So it is aligned and exposed to the UV light. Then it is again baked and developed. This solution will be developed because when we align this, this pattern will be generated over this, but we cannot see this pattern. So it will be developed with the help of some developer solution. Then this over from here your silicon dioxide will be removed, and finally your PR will be removed. The function of the PR is now complete, so we can remove the PR, and then after post bake we can now this is ready for the next steps, right? So these are the steps which are carried for any lithography process. So the first step is the substrate preparation. Under this substrate preparation, we intended to improve the adhesion of the photoresist material to the substrate. This is accomplished by one or more of the following steps. For example, we have to clean the substrate cleaning, which is done to remove the contamination. Okay, baking, so that if some water molecules are precipitated on the substrate or inside the substrate, that should be removed. It is done with the help of baking. Then addition to that, the adhesion prometer to keep the water away from coming back, right? Then the substrate contamination can take from the from particulates or a film that can be either organic or inorganic, and this will also form the irregular pasting of the photoresist material. So this should be removed, so that we can have a better pasting and the better line width control. So one type of contamination is the absorbed water. It is removed mostly by baking the substrate at a high temperature. It is also known as dehydration bake. And the dehydration bake, as the name implies, it removes the water from the substrate by baking the substrate at 200 to 400 degrees C, and this process is carried out for 30 to 60 minutes. Then the substrate is allowed to cool, and the coating will be done as soon as possible. This typical dehydration bake does not completely remove the water vapors from the substrate. So next is if we have the silica substrate, then we may have silicon, polysilicon or silicon dioxide or any other substrate. It may have the silane groups, right? These silane, when the water molecules form with react with the silicon surface, they create a very strong mono layer of water, forming the silane group, that is known as SiOH group. So the preferred method to remove those silane group is by chemical method. So in this chemical method, the surface silane is replaced by OH group with an organic functionality group, that is unlike the hydroxyl group, which offers a very good adhesion properties to the photoresist material. And the silanes are often used for this purpose. So the most commonly it is known as HMDS. Next processing step is, now your wafer is very much clean, no particle contamination is there. Now your next step is we have to paste the photoresist material over that substrate. So very thin uniform coating of photoresist material, well controlled thickness, is done with the help of spin coating process. The photoresist it is in a liquid form. If it is not in a liquid form, it is converted into liquid form, and then we put the substrate in that liquid, and then it will be processed for the baking, right? So it is done by pouring the PR material on the wafer. It is then spun on a turnable table at a very high speed. So we have a table, over that your substrate will be there, and we have to pour the PR material so that PR material will be spun equally all over the substrate. Now to achieve the desired thickness and the uniformity, there is a choice between, we can have this static dispense. In case of static dispense, your wafer will be stationary and your resist is dispensed all over the substrate. Okay, wafer will be in stationary position. But in case of dynamic dispense, the wafer will be spinned. The wafer will be continuous spinned. It will be on the turnable table, and your resist is in the stationary form, and then it will be spread all over the substrate, because your wafer is rotating, and the spin speed and the time of rotation and the acceleration of each spin will give you a uniform thickness. So with the help of these three parameters, that what is the acceleration, what is the speed, spin, and what how many times we are going to spin the turnable table, that all will give you the that how much thickness of the PR is going to apply on the substrate, right? So so when we if we have the very much high speed, right, suppose we have a very thick liquid and we rotate the substrate at a very high speed, that PR will be spread all over the wafer, right? So initially, if your PR is like this, right, if you rotate it on a very high speed, it will be spread like this, right? It will be spread like this, and finally we are going to have a very thin layer. So if you increase the RPM of the RPM, then the viscosity, depending upon the viscosity, the thickness of the resist will be decreased. So here we have the resist thickness at y-axis, that is in micrometer, and here we have the spin speed, that is in RPM, right? So thickness, we can see in the graph that it is decreased. If we have the low speed, it will be very high thickness. If you have the very high speed, it will be decreased gradually, right? So photoresist spin curve is an essential tool for setting the spin speed to obtain the desired resist thickness. And finally, the resist thickness varies inversely with the square root of the spin speed and is roughly proportional to the liquid photoresist viscosity, right? Next is, after applying this PR material, we have to bake that wafer, so that the PR which is in the liquid form, it is properly in the dry form, and it is properly pasted over the substrate. So after coating, the resulting resist film contain 20 to 40% solvent by weight, right? The post apply bake process, it is also known as soft bake or pre-bake, which involves the drying of photoresist material after spin coating to remove the excess solvent. There are four major effects of removing this solvent from the photoresist film. The first one is the film thickness. The film thickness will be removed if you dry that material, right? Post exposure bake and development properties will be changed, adhesion will be improved, and the film become less tacky and thus less susceptible to the particle contamination, right? Obviously, if we have the liquid material, more particle contamination will be attracted towards that, but if that material is dry properly, then we can have the less contamination. The chances of contamination will be less. Now, for this chemical applied resist, the residual solvents can significantly influence the diffusion and the reaction properties during the post-bake process, right? So, depending upon the photoresist material which we are going to use, for that we have to control the temperature. For example, we have this DQN, that is no lac resist, which is generally baked at about 70 degree. And if you bake above that temperature, it will start decomposing, right? The PR material will start decomposing. So for each PR material, we are going to have a very specific temperature. This is one example. And the most popular bake method is the hot plate method. It is also known as the proximity baking. The wafer is brought into the close proximity for about 100 micrometer gap to a hot plate. with a very high mass, very high hot mass plate. This is the hot, suppose this is the hot plate, and here we have the wafer. So they are come in proximity with the distance of 100 micrometer, and this process is done only for 20 seconds. Then the wafer is removed from the hot plate, and baking continues as long as the wafer is hot. Now, after that hot process, the plate is allowed to cool, and it is kept slightly below the room temperature. Next step we have is the alignment and the exposure. Now we have applied the PR. Now that PR material is dried, right? So we have this silicon dioxide, we have this PR material which is applied, and it is now in the dry form. It is properly dried with the help of baking process, right? So the next step is align and exposure. Now we have to, what we have to do, we have to expose this to mask, right? We have to expose this to mask. So mask alignment, it should be proper when it is exposed to UV light. So this mask alignment can be done in two ways. First one is the contact, and the another one is the proximity way, right? So depending upon that, we can have two lithography process. We can convert it into two lithography process. First one is the contact lithography, and the another one is the proximity lithography. These are the simplest method to expose the resist pattern to the mask. So in case of contact lithography, it offers a very high resolution, but the mask damage and the which results in low yield and make the process unusable in the further production environment. Okay, so what we are going to do here, in case of contact printing, this mask and this PR material, they are very close to each other. But in case of proximity printing, they are kept at a certain distance, and the chances are the mask damage will be less, but the alignment issues will be there. So it will remove the it will reduce the resolution, and unfortunately this resolution limit is increased to greater than 2 to 4 micrometer, right? So in case of contact printing, your mask will be damaged, and we are not going to use that mask for the further processes. But in case of proximity, we may have less resolution, but the mask can be used for n number of times, because it will not be damaged. So by far the most common method of exposure is the projection printing. In case of projection printing, we have to use one lens, and the image will be projected on the wafer with the help of that lens. So this is the example of contact printing. Here, in case of contact printing, here we see this is the silicon substrate. Here we have the SiO2 layer, and over that we must have the PR, and here we can see that the mask and the PR material, they are in touch with that. So in case of proximity printing, there is certain distance between the mask and the PR material and the substrate, and in case of projection printing, we have the lens. This is the lens, right? And whatever the pattern we have to draw over there, that will be projected with the help of this lens, and it will be projected over this substrate, right? With another diagram, here we can see that in case of contact printing, we have this light source, some lens is there, and this mask is in contact with the photoresist material. And in case of proximity printing, we can see that we have the lens, and there is some distance between the mask and the substrate. And with the help of this lens, we are going to imprint the pattern on the substrate. Next processing step is the post exposure bake. So now we have the mask, and now we are going to expose this to UV light. Okay, we are going to expose this to UV light. So when it is exposed to UV light, the properties of this PR material will be changed depending upon whether you are using the negative PR material or positive PR material. Some portion will be softened and some portion will be hardened, right? So post-exposure bake, monochromatic light when projected on the wafer, it strikes the photoresist surface over the range of angle approximating plane waves. The light travels down the photoresist material, and if the substrate is reflecting, it will be reflected back through the resist, right? If your PR material is the reflecting material, it will be reflected back, else it will be absorbed inside the material, right? And the incoming and the reflected light interference to form the standing wave pattern of high and low light intensity with a different depth in the photoresist material. Now after this we have to develop the pattern. So after development, this pattern is replicated in the photoresist material, causing the undesirable ridges in the side wall of the resist feature. So one method to reduce the standing wave effect is known as the post exposure bake, PEB. It is done at a very high temperature, generally at 100 to 130 degrees C, which smoothing out the standing wave ridges. And for conventional resist, the main reason for the PEB is to remove the standing waves which are because of the reflection or the another incidence rays. So once it is exposed to the UV light, your photoresist must be developed. The most photoresist material use the aqua base developer solution in a particular, for example, we have it is tetramethyl ammonium hydroxide, which is commonly known as TMAH, is used at a concentration of 0.26 in it is used in the developer solution to improve the wafer wetting during the development. This method of applying developer to the photoresist is important in controlling the development uniformity and the another process latitude. So during the spin development, the wafers are spun using the equipment similar to that we are using for the PR material. For the application of PR material, we have to rinse the substrate inside the developer solution, and then we have to dry that. So here we can see that this is the spray technique and the puddle technique. So another technique in case of spray, in case of spray method, we have the substrate and your developer solution is spread all over the substrate, and in case of puddle method, we have this puddle. We are going to keep the developer solution in a stationary motion, and it is a turnable table. It is and then this developer will be spread around the wafer. Then it is spinned and dried. Next is the pattern transfer. Now we have the pattern, the mask which we have used in the previous steps. That mask pattern will be imprinted on the substrate, right? So a post bake, it is also known as the hard bake. It is used to harden the final resist image so that it will withstand with the harsh environment of a particular transfer process. Next, it is exposed to high intensity deep UV light that can be used to cross link the resin at the surface of the resist, forming a tough skin around the pattern, which is used to allow the photoresist to withstand at the high temperature of 200 degree C. Sometimes plasma treatments and electron beam bombarding had also been used to harden the photoresist material. Okay, so after this post bake, the hardened resist is often subjected to resist etching, that is known as D-skim etch. During this D-skim etch, a very thin layer of about 20 nanometer of the photoresist material is removed. So if we use the contact printing or the proximity printing, the minimum line width that can be imprinted, it is denoted by LM. It is given by lambda G, under root of lambda G, where lambda is the length of the exposure radiation, G is the gap, G is the mask and the wafer gap, which includes the thickness of the resist. Okay. So for typical values of lambda that approximate 0.4 micrometer and G approximate 50 micrometer, your LM will be 4.5 micrometer. So next process we can use is sometimes here we can see that in order to include the problems which are associated with the shadow printing or the projective printing, some exposure tools we can use to develop the or project an image of the mask pattern onto the resist coated wafer, which may be kept at a few centimeter away. A small image area is scanned or stepped over the wafer to cover the entire surface. The resolution of the project system is given by the formula LM is equal to lambda divided by NA, where lambda is the wavelength of the exposure radiation and NA is the numerical aperture, which is given by N sin theta. This NA is equal to N sin theta, right? So here we can see that we have the small, we have this complete marks. The small portion is exposed. It is passed through the lens. With the help of this lens, it is projected over the wafer, right? So here we can also see a very small portion. This portion is projected and it is patterned over the substrate, right? Here we can use the, we can see from the picture, it is the step and repeat method. Here we have a very small mask, right? So that pattern is repeated n number of times. Here you can see first pattern, second pattern, third time, fourth time. So n number of time this pattern is repeated, right? Similarly in this case, it is again we can do that in vertical direction or in horizontal direction depending upon the requirement. So we can have a very small pattern also, we can have a large pattern. From that large pattern we can draw the very small window, or we can project a part of the mask which can be imprinted over the substrate. So N denotes the reflection index of the image with the image medium. If N is equal to 1 in air, this theta half angle of the cone of the light covering to the point image wafer, this depth of focus delta Z, it can be given by plus minus LM divided by 2 tan theta, that is approximately equal to plus minus LM divided by 2 sin theta, and that will be equal to plus minus N lambda divided by 2 Na square. Okay. So the resolution can be enhanced by reducing the lambda, and this explains the trend towards the shorter wavelength in the optical lithography. Typically the scanning projection systems are capable of about 1 micrometer resolution. With the help of these scanning tools we can have the resolution of about 1 micrometer, while the step and repeat projection system can be accomplished to where we have to work on deep sub-micrometer technology, and we need a very high resolution integrated circuits, especially when they are coupled with the UV radiation sources. So next portion we are going to cover is the photoresist material, that what are the photoresist material which we are going to use for this optical lithography. So this photoresist material that can be classified into two parts. First one is positive PR and the second one is negative PR. The second one is negative PR. In case of photoresist, if your photoresist is radiation sensitive compound, for positive photoresist the exposed region become more soluble, and it is thus more readily removed in the developer solution. Okay. So, in case of positive photoresist material which is exposed to UV light, that will be soft and it will be more soluble in the etching solution, and that will be removed at the time of developer. Okay. Whereas in case of, so in case of positive photoresist material, whatever mask we are going to use, that that exact replication of that mask will be imprinted over the substrate. But in case of negative PR material, the opposite of that will be imprinted over the substrate. Okay. So this is the case of positive and negative photoresist material. In case of positive photoresist material, here we have the mask like this, right? It is we have to etch from these sides, so it is protected over there, and from this side your material is etched, right? And in case of negative photoresist material, we have this mask, right? UV light is passed over this, so that portion is saved and the opposite of that is imprinted. From here it is removed, the silicon dioxide is removed from here. So, in today's lecture we have seen that how the optical lithography works, that when your PR material is sensitive to UV light, we use UV light as a source, we can say that it is optical lithography, right? And we can have three types of optical lithography. In that, we can have the contact printing, we can have the projection printing, and we can have the proximity printing, right? So, depending upon the application or the requirement or the resolution, we can choose any type of printing. And what are the PR materials? So, depending upon that PR material, we are going to draw the pattern on the substrate. So, thank you so much. I hope you like the lecture.